Have you ever stopped to think about what's really going on inside your phone or your laptop? It's not magic, not really. It's actually a conversation, one that's happening in a language made up entirely of numbers. And today, we're going to learn its language.
So, let's start with a puzzle that feels a little bit like a magic trick. How in the world does a calculator take 5 minus 10 and spit out -5? I mean, it's just a bunch of on and off switches, right? Where does the minus sign even come from? That's the core mystery we're cracking today.
To get to the bottom of that, we have to start with the basics. We need to learn a computer's native language. This is a journey that'll take us from the numbers we use every day, right down to the actual electrical pulses zipping around inside the machine.
In that language, it's called binary code. You know, at the end of the day, a computer is just a massive collection of billions of tiny little switches. They can be either off or they can be on, and that's it. We just use a 0 for off and a 1 for on. Literally every single thing your computer does, from playing a video to sending an email, boils down to a super long sequence of these zeros and ones.
Okay, so you and I, we live in a base 10 world. We've got 10 digits, 0 through 9, to work with. Computers, though, they're stuck in base 2 with just that 0 and 1. But here's the really clever part. That super simple base 2 system, it acts like a universal translator. It helps the computer talk to other number systems that are way more convenient for programmers, like base 8, that's octal, and base 16, which we call hexadecimal. So check this out. If a computer wants to translate from one of those systems, say base 8, to another one, like base 16, it doesn't just do a direct conversion. Nope. First, it translates the base 8 number into its own native language, binary. Then, it takes that binary code and translates it into base 16. You see? Binary is the essential middleman, the bridge that connects everything.
All right, let's actually see this in action. Say we have the number 232 in base 8. The computer looks at each digit one by one and converts it into a little 3-bit binary group. So that first 2, that becomes 010. The 3 becomes 011. And the last 2, well, that becomes 010 again.
Now for part 2 of this translation, the computer takes that long string of binary we just made and it reshuffles it. This time, it groups the bits into chunks of 4, getting it ready for base 16. And when you translate those new 4-bit chunks, what do you get? You get the hexadecimal digits 9 and A. And there you have it. 232 in octal is now 9A in hexadecimal, all thanks to binary acting as our go-between.
Okay, that's pretty cool. So computers have a way to represent numbers. But that's just one piece of the puzzle, right? How do they actually do anything with them? How can a machine add or subtract when all it has are zeros and ones?
You know, the rules for adding in binary are surprisingly simple. In fact, they're almost boringly simple. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. Okay, no surprises there. The only one that's a little different is the last one. 1 plus 1 equals 0. But you have to carry the 1 over to the next column. It's the exact same carry the 1 you learned in grade school, just way, way simpler because you only have 2 digits to think about.
And by just applying those 4 simple rules again and again, a computer can solve any addition problem you give it. It's just a simple mechanical process. Add up the column, carry the 1 if you need to, that's it. This is literally the foundation for all math inside a computer.
All right, addition makes sense. But this brings us right back to our big question from the beginning. We only have zeros and ones. There's no minus symbol. There's no switch for negative. So how on earth do you represent negative numbers?
Yeah, this is the real challenge. The computer's entire alphabet is just 0 and 1. It has to find some clever way using only those 2 symbols to show the difference between positive 25 and negative 25.
And the solution they came up with is just brilliant. It's so elegant. We take the very first digit in a binary number, it's called the most significant bit, and we give it a brand new job. From now on, that first bit isn't a number anymore. It's the sign. If it's a 0, the number is positive. If it's a 1, the number is negative. Simple as that.
But, you know, just saying okay, the first bit is the sign wasn't the end of it. The pioneers of computing actually came up with a few different ways to make this work. And it's this really cool evolution of ideas as they tried to find the perfect system.
So the first try was called sign and magnitude. Super straightforward. First bit is the sign, the rest is the number. But it made doing the math a total headache. The next idea was ones complement. This involved flipping all the bits to make a number negative. That was better, but both of these early methods had the same huge problem. They had a way to write positive 0 and a way to write negative 0. That's just confusing and a waste of space. And then, along came 2's complement, which, you guessed it, finally cracked the code.
So, why did 2's complement come out on top? Why is it the standard that pretty much every single modern computer uses? What was its secret sauce?
Well, it really boils down to 2 things. It's efficient and it's elegant. First off, 2's complement gets rid of that whole negative 0 problem. There's only one way to write 0, no confusion. But the real game changer is that it lets the computer do subtraction by just doing addition. This little trick makes the physical circuits inside the computer so much simpler.
Okay, so let's put this winning system through its paces with one last puzzle. We've got this 8-bit binary number here. Now, look at that very first bit, the sign bit. It's a 1. So right away, we know this has to be a negative number.
But what negative number is it? I mean, that's the real question, isn't it? Knowing it's negative is great, but which one? How do we decode 11101011 back into something that makes sense to us?
To figure it out, we just run the process in reverse. It's a simple 3-step recipe. Step 1, take our negative number. Step 2, invert every single bit. Flip all the 1s to 0s and all the 0s to 1s. And for step 3, you just add 1 to that new number you just made.
And after you do all that, what do you end up with? The binary number 000100101. And if we translate that back into our normal everyday base 10 system, it's the number 21, which means our original mystery number 111011011 was just the computer's clever way of writing negative 21. See, it's a complete, totally logical system.
And that leaves us with one last kind of mind-blowing thought. We've just seen how a simple on-off 0 and 1 language can build a system for all of mathematics. So if something as abstract as a negative number can be built from these simple little switches, what else can be? Think about it. Letters? Colors? Music? The answer, of course, is everything. Everything you're seeing on this screen right now.